So you guys are on worksheet 1B. At the very top, they give you what is called a piecewise function. So the way you read a piecewise function, it's a function that's not continuous, and it's split amongst different parts of the domain. So the first piece of your piecewise function is right here. It says it's the square root of x plus 1 if your x's are less than or equal to 4. So if you're plugging in or evaluating at something smaller than 4, you're going to use that function. Now, the next part of the piecewise function is the function 3x, but you only use that if your x's are between 4 and 10. Notice there's no equal to bar there, so it's not including 4 or 10. And then the third piece of your piecewise function is this guy, 2x squared minus 15, and you only use that piece if your x's are greater than or equal to 10. So our first task is just evaluating piecewise functions. We will eventually come back and graph them, and then eventually we're going to write piecewise functions, which is a hoot. But for now, let's just go ahead and evaluate them. So when they say g of 1, that's their fancy way of saying plug in x equals 1. Are you going to be using the top, middle, or bottom function if x equals 1? It's the top function because it says use me if your x's are less than 4. 1 is clearly less than 4. So, top function, could you please, come on pen, plug in x equals 1. So you have the square root of 1 plus 1, better known as 2. And then same function, but this time I want you to evaluate at x equals 3. So are we using the top, middle, or bottom function? Top again. So x equals 3 into that blue function would be the square root of 3 plus 1, and this is a funky number because square root of 3 is irrational. So like, is it 2.7 or something when you type it? I think square root of, yeah, okay, close enough. So it's about 2.7. What if x equals 6? Top, middle, or bottom function? Yeah, plus 1. When we're plugging in a 6, are we using the top, middle, or bottom function? Middle this time, because 6 is between 4 and 10. So using my middle function, which just says 3 times your x, 3 times 6 is 18. And what about plugging in exactly x equals 10? Bottom function this time, because it does say that if your number x is greater than or equal to 10, you must use this bottom function. So 2 times 10 squared minus 15, negative, no, 185? Okay. That says 185. It's on the corner of the screen. You can see it. So, piecewise functions. They're exciting. Let's look at more function evaluation, more that's like inspired by your homework, but also what's going to be on your test. By the way, your summative this week is Friday. The summative is going to cover all of this new stuff we've been covering. And remember, there's a couple things in quadratics that we haven't tested yet. Those cut the corners of the box problems. Remember those? Okay. And what else did we do? Oh, the applications, just solving things on your calculator with quadratics. So it's a lot of that. This old stuff on quadratics, I'm not retesting that on the next one. So that's up to you guys to do every take. So we have a function. This is a quadratic. And I want to evaluate at -1. So you can use your calculator because it is a Monday. Go ahead and plug in a -1 everywhere you see an x. Let's see, that's 1 plus 8 plus 1. Would that be a 10? Can I add today? Oh, good. Go me. All right, now we're going to plug in some algebra into your function. So this time, instead of getting like a numerical answer, you're going to get an algebra answer. So I like to draw the skeleton of my polynomial or my function. And then in place of all the x's, I'm going to place whatever they want, which in this case would be a 2x. And then it is your job to simplify this to the best of your abilities. So 2x squared as a quantity would be 4x squared, and then minus 16x plus 1. So you'll notice when you have a function like this, and I ask you to evaluate at an algebraic expression, you're not going to get a pretty numerical answer. You're going to get something like that, usually. This is fun. Let's plug in x plus 8. So, quantity squared minus 8 times the quantity plus 1. Well, you're supposed to plug in x plus 8. Now, this is where I get a lot of kids. They think x plus 8 squared is just square everything. But that's not how binomials work, right? X plus 8 squared means x plus 8 times another x plus 8. So you need to FOIL this out. This is x plus 8 times x plus 8, which is x squared plus 16x plus 64. And then keep going because you have the whole rest of this expression. So we have negative 8x and then a minus 64. And then you still have that plus 1 off to the side. So not a math teacher on the planet who'd be happy with that answer, guys. Let's collect our like terms. There's only one x squared. Right here you have 16x minus 8x, so we call that plus 8x. And this is kind of neat. The 64's cancel. And then plus 1. That's pretty. There's one just like that on your test. Except I think it's harder. Because I threw like a 3 in front. Ha! What would happen if I put a 3 in front of this function? When do you distribute that 3? After we FOIL it out, yeah. That's the kicker. A lot of kids try to distribute it like right away, and it doesn't work that way. All right, more piecewise fun. So we have 3 pieces to this particular function. This first piece is used when your x's are less than 3. This middle piece is used if your x's are between 3 and 8, when equal to 3 but not equal to 8. And then this last function is weird. It's just a constant 42 if your x's are greater than or equal to 8. So, what if I'm plugging in x equals 3? Am I using top, middle, or bottom function? Middle that time, because it is exactly equal to 3. So we have 2 times 3 plus 10, which is 16. How about 8.5? Yeah, that bottom function, which is a weird one because it's constant. Like, how do you plug into a constant function? Like, you don't, because it's always 42. So the answer is 42. I like those. Those are nice. Remember seeing those in Algebra 2, though? And then kids would always, like, put extra work into it. And you're like, no, 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 no. It's just 42. They're like, 42x? No, 42. Oh, Algebra 2. You guys were so silly last year. All right. We already covered the rest of these notes, I believe. So next task, I need you to find Worksheet 2B. Haha, good joke. I appreciate that one. Now, when you find Worksheet 2, the front should make you nervous because it's piecewise applications. Let you be nervous about that on a different day. Today's not our day. I need you to find the back of Worksheet 2, which starts off with what's called rate of change. So this is like your beginning of pre-calc introduction to a calculus concept. Remember, the title of your course is Pre-Calculus from a Calculus Perspective. Like, that's scary sounding. So we're trying to introduce you to the concepts that will show up in calculus, and we're giving you like the very basis of how they are formed. And then at the end of our pre-calc course, we'll come back and talk about rate of change. We'll talk more about instantaneous rate of change later. But we're going to introduce you to it today, and then you'll kind of get a feel for what the whole point of calculus is, at least for part of it. So don't let this notation scare you, because let's break it down. Rate of change says between x equals something and x equals something else, so a and b, the function changes. And then what does it mean when they say like f of b, f of a, f of x? What is synonymous with your Algebra 2 life whenever we said f of x? What was the same thing as saying f of x? It's just y. So this formula right here, is saying function evaluated at b minus function evaluated at a. That kind of feels like y2 minus y1 over x2 minus x1. Guys, this is just slope. So they're giving you what is typically not a linear curve, and they're asking you to find slope between 2 ordered pairs along that curve. And we're going to find out what happens when we get closer and closer and closer to the actual ordered pair that we're looking at. All right, so for now, we have a function, 3x minus 4, and they want me to find the average rate of change from x equals 3 to x equals 8. So when you plug in 3 into that function, so plug in a 3 right there, you get 3 times 3 minus 4, you get a 5. And then when you do that same work, but you plug in x equals 8, so we're evaluating f of 8. You get 3 times 8 minus 4, which is 20. Thank you.
Where did you get 12 from?
I don't know, but I was going to go with it, so I'm glad they corrected you. All right, so we have two ordered pairs, and I'm supposed to find average rate of change, which I now know means find slope. So here we go. 20 minus 5 over 8 minus 3, which is 15 over 5. So our average rate of change, oh yeah, is 3. Ta-da! Isn't that lovely? So same idea, but this time I give you this beautiful quadratic function and two different ordered pairs to go from. So when x equals 2 and when x equals 4, I need you to figure out what's going on. So 2 squared plus 6 times 2 minus 10. Oh boy. 12, 6. I don't know, I'm really scared now. Is it 6? Saw some head bobs. Okay, good. And then if I plug in a 4, let's see, 16, 24, 40. Is that 30? Awesome. So I have my two ordered pairs at those two particular x values they wanted, and now I'm going to find slope. Average rate of change would be 30 minus 6 over 4 minus 2, which is 24 over 2, which is 12. Yeah. All right, cool. So that's basically the idea. The end of your homework assignment, there's some instructions where it says, like on number 66 or whatever, change the instructions from the book and find average rate of change from x equals 1 to x equals 3. So that's all you got to do for it. But let's dive a little deeper into the idea of rate of change. So this is the calculus concept of it, and this is probably a picture from your textbook. We're going to take a curve, this little curvy guy here. And when I ask you about, like, what is the average rate of change, that's really asking for slope if it's intended to be a linear function. But if I ask for these random two ordered pairs that are really spread out, the slope of the line that connects those two ordered pairs doesn't really match up with the curve very well at all. I mean, I know I don't draw really well, but even I can see, like, no, those are not the same thing. So this is really leading into a concept that's called a tangent line. Not the same tangent that you guys are familiar with, a different tangent, but they do have similarities. We'll talk more about that later in our pre-calc course. So how do we fix this? Because I can tell that that line, that average rate of change line between those 2 points, is not really reflective of what's going on the function itself, the curve. So think about this function. Not the same function they've graphed there, totally different function. Y equals x squared. What is that? What does that look like when I graph it? It's good old basic parabola, right? Phew, one of these. Oh, that was almost good. My question to you, which part of the function would have a larger rate of change? Between x equals 0 and 1, or between x equals 4 and 5? So between x equals 0 and 1, I'm just kind of estimating off of my picture. The line that would connect these two red points would be like this. But when x equals 4 and 5, I mean, we're talking like up here. Actually, way further than that, but pretend. Now that you know average rate of change is synonymous with slope, can you tell me which one has a larger average rate of change? Blue or red? Blue has a much larger slope. Slope would be the steepness of the line in this case, and it gets way steep. Now think about the function itself. You're squaring your input value. So if you start coming up with much larger input values and you square them, that number's going to get bigger and bigger and bigger and bigger, while the denominator doesn't really change because you're still 1 unit apart. So when I look at the curve and we come up with what's called a tangent line in the future, you can physically see which one has a steeper tangent line. But the math works out the same, guys. So you can always go old school and calculate the average rate of change for now in pre-calc. So talk to me about these three functions. F of x equals x. What's that? If I were to graph it. It's just a line, isn't it? Like with a slope of 1 and goes through the origin? Okay, boom. And then what about g of x equals x squared? We just found out that was our friend the parabola. Okay. Beautiful. As always, Abruzzo. Nice job. And then who remembers what the cubic function looks like? Yeah, the weird squiggly dude, like this guy. So they're curious if you can identify which one of those functions has a greater rate of change, average rate of change, between x equals 2 and x equals 3. Off the top of your head, anyone have a thought? Which one would have a steeper line? I know. Don't look at the origin. Look a little bit to the right of the origin. The cubic. Yeah. It's going to be way steeper, actually. And you know what? Just for funsies, let's go ahead and calculate it. X equals 2, and you guys said you wanted to calculate. I'm sure you did, right? So the green function here, which is f of x equals x. When x equals 2, you plug in a 2. That's really boring. You get back a 2. And then when you plug in a 3, you plug in a, okay, it's a 3. So this was really dumb of me. Why did I even calculate this? I knew his slope was 1. Guys, it's a line with a slope of 1. This was silly. All right, 3 minus 2 over 3 minus 2. Okay, so 1. Cool. All right, blue function, which is x squared. If you plug in a 2 to this blue function, you get a 4. If you plug in a 3 to that blue function, you get a 9. And when you calculate slope, average rate of change, you get 9 minus 4 over 3 minus 2. So you get a slope of 5. Average rate of change of 5. And then for my red, the cubic function, when you plug in a 2 and then you cube it, you get an 8. When you plug in a 3 and you cube it, you get a 27. Okay. I'm seeing where you're going now. That got real big. 27 minus 8 over 3 minus 2, which I believe is a 19. Yeah, much bigger rate of change. And even with my really terrible drawing, you can even see the slope would be much higher on the red function. All right. So we're going to go dip our toes into calculus for a moment. This would be fun. Find the average rate of change for our fun quadratic function, x squared, really boring function, between these two intervals. So from 1 to 1.1. So the first ordered pair would be when you plug in a 1. So 1 squared is 1. And then here I'm going to need some calculator help, guys. What happens when you plug in a 1.1? What's 1.1 squared? 1.21, thank you. So let's go calculate some average rate of change here, y'all. 1.21 minus 1 over 1.1 minus 1. My rule is if there's a decimal involved, I don't do an ounce of math in my head, because I ruin it every time, so please calculate this. Is it 2.1? Okay. So same question, but now we're going to change the second x value a little bit. So I still want to use the ordered pair 1, 1. But the second ordered pair is 1.01. Can you plug that in for me? I know it's got some zeros. 1 point, is it 0201? Yeah. Okay. So finding average rate of change between these two red points. I just want you to know how painful this is for my dyslexia. This is like torture. This is absolute torture. And I didn't record last hour because I knew that I'd invert all these decimals. So I saved it for you. All right, what'd you get on this one? 2.01. Okay, good. Awesome. All right, almost there. Now let's try plugging in a 1.001. Here we go. Is it 1.00? No, no. Yeah. 00? Yeah. 2001? Yeah. Ha. All right. So average rate of change between those 2 points. Okay. 1.002001 minus 1. See, I could never be a computer programmer with binary. It'd be like 1001. I wouldn't be able to do it. All right, what you got here, guys? Let me guess. 2.01 or something. Or 001. It's like I sense a pattern, Abruzzo. All right, so what's happening here? Look at your outcomes for the average rate of change. when the points were relatively close to each other, 1 and 1.1, I got 2.1. And then when I got even closer together, it became 2.01. And then even closer yet, I got 2.0001. Now, we stopped this fun, but I could have kept it going. We could have plugged in like 1.0001 and then 1.000001. And what do you think would be happening to our outcomes every time? They're going to get closer and closer and closer to 2. Yes, because that is what's called the vocab word, instantaneous rate of change. So that's a calc concept. You don't have to ever remember that for like 11 months, okay? You can forget it. Instantaneous rate of change is what that concept is called, but we will come back and discuss this later. All right, find the instantaneous rate of change for this guy. Now, I'm not going to manually plug in like 3.01, 3.001, 3.0001. I'm going to use my calculator. So I want you guys to go to your calculator and type the function 3x squared into y equals. Apparently I already did it. But then I want you to go to your table, and we're going to set up the table to be in what we call ask mode. That means I control what the x's are. It won't automatically fill them in. So I'm going to choose some weird funky x's. So when after you get your function typed into y equals 3x squared, go to table set, which is above window, and make sure your independent is in ask mode. That's all you need to be careful about. Well, dependent should be in auto, but independent is in ask mode. And then I want you to go to your table, and depending on, oops, what is this doing? Okay, I think I'm like crashing my computer screen. Go to your table, and then I want you to type in the following x values. Please type in 3.01, 3.01, 3.001, and 3.0001. Can you guys tell me what you got for a y value when you typed in 3.01? And then what about 3.001? And what about 3.0001? 00. Do you have a feeling it was really 0.18? Yeah, they truncated it. I bet if you highlight it, it'll show you 18. All right, so I know your screen truncates it to a 2, but if you highlight it, it'll show you the 1.8. Yeah, sneaky little devil. All right, I sense a pattern. Anyways, what do you feel like it's trying to approach over here in the y's? It's approaching 27, right? Okay, so we still need to find, the answer is not 27. I need to find still the instantaneous rate of change around x equals 3. So it doesn't really matter which two ordered pairs you use, but the closer you are, the better. So I'm going to use these two, and I'm going to find slope. Here we go. 27.0018 minus 27.018. And you should get real stinking close to 18 when you type that in. I know you guys are getting your bifocals out so you can see all those zeros. So that's kind of neat. Now what's extra neat is when you go on to calculus with Mrs. Gupta or whoever you have for calc next year. Like if you're going to college, obviously she won't be there. But she is going to teach you some neat calculus theorems that help you calculate all these things without having to go grab a table and evaluate a bunch of things. So calculus is like wizardry. It's amazing. You didn't get 18?
I got
a power answer.
when I subtracted 3.00.
Did you put parentheses around? Haha, that'll do it. Alright, so, I bet you think we're done, right? Ha! Fools. We are not done. Now I need you to find worksheet 3. Just keep your eye on the prize, guys. We're looking for work days next week. Homecoming week. It's crazy. Y'all are wearing weird clothes. No one can concentrate.
Wearing my normal clothes.
I still don't know what to do for meme day. I I think I'm just gonna, I have one t-shirt that is a meme. I think I'm just gonna wear it. It's my favorite t-shirt, so it works.
Is it a mapping?
It is, kind of. It has a really cute Scottish fold cat. And it's holding a pencil, and it's got glasses, and it says, "Stop animal testing." It's adorable. Alright. Can y'all find worksheet 3? So, this whole unit it's really quite hard for Hoffbauer and myself to plan, because all the topics kind of blend into each other, because it's functions, which is a really broad topic in PreCalc. So what we're going to do on 1.2 is we're going to be analyzing graphs of functions either through what we call inspection, which is just looking at something that's already been graphed for us, and estimation, but then also we're going to take an algebraic approach on some of our simpler functions. So we have to really get our vocab down in order to be successful on this part of the lesson. So this paragraph is somewhere in your notes. I would do some highlighting or some marking. There's some important pieces of information here, guys. Y'all know about domain and range. We talked about that the other day, and you've talked about it for your entire career in Algebra 2. But the x and y intercepts, we got to remember how we find those for functions. So the x-intercepts, which also are known as zeros, and by the way, they also are known as roots, FYI, they are where the function's input values produce an output of 0. So it's where it gives an output of 0. So that's a really fancy way of saying set f of x equal to 0 and solve. But that's kind of how we find solutions, right? We set it equal to 0 and solve. Now, don't confuse that with y-intercepts. The y-intercept is where x equals 0 on your function, because it's where it crosses the y-axis and x equals 0. So that's a fancier way of just saying plug in x equals 0 and then evaluate or compute. So, here we go. This one's already done for you. This is straight out of your textbook. So, you don't have to do much looking. You just have to kind of match it up and say, yeah, that's exactly what I was going to say. So remember this set builder notation for domain? We're not going to be using set builder, so don't freak out there. But would you guys agree that the domain of this function is indeed negative infinity to infinity, because it stretches forever from the left to the right? The other comment they made is about range. Remember, we're not doing set builder, but their range goes from negative infinity and then up to 5.0625 with a bracket. The only reason they were able to tell me that is because they either found the maximum through technology or they found the maximum through algebra, but they did tell you the maximum ordered pair right here. Now, why did they use the 5.0625 and not the negative 0.075 or 0.75? Because range is the y, not the x, right? So they have to use the y value for range. And then here they did a little bit of work. First they estimated. They said, let's go find all of our, well, first they did y-intercept. So when I look at this graph, maybe you guys would have estimated that it crossed the y-axis at 4.5, but we're pre-calc. Estimation's not good enough. We're going to have to then confirm it algebraically or through technology. So what they did then is they plugged in x equals 0 into their function. And what do you know, guys? They got 4.5. So their estimation skills were on point. Yay. And then they said, further, I need to estimate the x-intercepts. So when I look at the graph, I'm kind of feeling like I kind of know where they cross. So if I was just estimating, I would have a good answer. But pre-calc, it's not good enough to estimate. So they would have to find the solutions through some other method. Now, your book got real fancy. And not only did it choose factoring for solving, it factored with fractions and decimals, which is not usually what you guys do. So I probably would have used another technique for solving it. But turns out the answers came out really nice to x equals -3 and x equals 1.5, which probably was what you were estimating based on the picture. But think back to all the solutions we've had in algebra and in pre-calc so far. Are they always pretty? No, in fact, they're rarely pretty. So joke's on us. Estimation is not going to work when I need a nice answer. Okay, that was very uplifting, Abruzzo. Thank you. All right, so this one is not done for you, but that is a nice little curve. It's a cube root function, and it has some transformations. We'll talk more about that next week, but transformations have occurred to it. I need you to find all this stuff. So let's start with domain. I know domain is how far left to how far right this function stretches. What you got? Negative infinity to infinity. Range would be lowest to highest y value. So how low and how high does this travel? It's also negative infinity to infinity. Woo! Come on, buddy. Last class they asked, is this going to be one of those moments where like everything is negative infinity to infinity? No. I know. That worked out a lot in Algebra 2, but not in PreCalc. Okay, next idea, the y-intercept. Remember the y-intercept, which you can estimate for me. Anyone have a thought where they think it crosses the y-axis? And I will warn you, it's counting by twos. Your book does this a lot, so watch out. Where do you think it's crossing the y-axis? I'm thinking it's at -8 too, but we got to confirm it. So how do we confirm the y-intercept? We plug in x equals 0. So you take your function, which they gave you right here, and you plug in 4 times the cube root of 0 minus 1 minus 4. All right, so this has to go first. Cube root of -1 is -1. So 4 times -1 minus 4, you guys are good estimators. This totally comes out to -8. If you wanted to write it as the ordered pair 0, -8, that is completely fine. All right, anyone have an estimate for where they think it crosses the x-axis? I think you're right with the 2, but you know, estimating won't be good enough for us. So now, to find the x-intercept, we're going to have to use algebraic methods to confirm. So x-intercept is when your function comes out to 0, so that means you're going to set your function equal to 0 and solve it. 4 times the cube root of x minus 1 minus 4. Okay. So, I think we'd start by adding our 4 over. And then you're going to divide that 4 coefficient out of there. So I have 1 equals the cube root. Don't overthink this, guys. How do you undo a cube root? You just cube it. So cubing this side, they go away. Cubing a 1 is very boring because it's just 1. So after all this work, I just got 1 equals x minus 1, and you were correct, dear. It is x equals 2. So you can just say 2 is your x-intercept, or if you want to get fancy and write it as an ordered pair, you would write 2, 0. Very good. I know, you don't believe me about them coming out funky. You're like, you know what, I'm just going to estimate it. Seems like they're always good. Yeah. This is where your teacher throws that out the window, doesn't she? This is where your teacher gives you that one example where it doesn't work. Here you go. Absolute value function. That's nice. Remember absolute value functions? They look like these. All these transformation things still apply. We'll come back to that later, but I want you to evaluate this function first graphically, and then I want you to confirm it algebraically. So if I was to plug in x equals -2.5, we'll plug it in a second. Let's look at the graph. Go over to where x is -2.5, and then go find the function and tell me what output you think this point has. How far up is it, though? Because I'm looking for the output. It looks like 12. So, like, is it 12? I don't know. We got to go confirm it. So, in your function, which is this dude, 2 times the absolute value of, we're plugging in -2.5 minus 3 plus 1. Okay, remember when you're evaluating absolute value expressions, you have to compute the inside first and then apply the absolute value. So this is -5.5, but what is the absolute value of -5.5? 5.5. So 2 times 5.5 plus 1, which is 11 plus 1. Got it, guys. It's totally 12. Good job, estimators. Let's try to estimate from the graph now for x equals 1. So go over to x equals 1, find the function, and can you estimate for me what you think the output is right there? And these are counting by 2's this time, so it's right between 4 and 6. So we're thinking it's 5, but we're not sure. We got to go confirm it. So 2, you're plugging in a 1 for the x. So absolute value of 1 minus 3 plus 1. All right, let's see. Inside first. So 1 minus 3 is -2. But you're taking the absolute value of that, so that's +2. You guys are excellent estimators. It is completely a 5. So you might be feeling very confident now, and you're like, you know what, Abruzzo, I'm just going to go estimate from the graph. What harm could it do? X equals 7. For sure, that has to be what? It's got to be 8. It's like right there. Boom. It's like dead on. Abruzzo, it's 8. I'm not even going to check it because you don't know what you're talking about. It's 8. It's 8. Except for you, you're going to check it, right? All right, 2 times the absolute value of 7 minus 3, plus 1. That's a 4 times 2, which is 8, plus 1, which is not 8. That'd be a 9, children. All right, so let this be a moral of your story. These pictures, they are just that. They are pictures. They are sometimes graphed well through technology, but they are also photocopied. And when you photocopy things, they shrink, they expand, they scale off of their normal scale. So you'll be looking at a picture going, I know for certain that is exactly at 8, and indeed it's not. So if you have the ability to check it algebraically, and I even tell you, like, you have to confirm it, I'm probably trying to trick you, so be careful. However, I will say that estimating off the graph is a cool trick, especially on a multiple choice test or an SAT test where you can eliminate some answer choices just based on what it looks like. So always a good idea. All right, domain and range. Remember, domain is left to right. So this particular function, be careful, they're counting by 2s. They do this all the time. It drives me bonkers. So can you tell how far to the left and to the right this function is going to stretch? What is this? Yeah, it's -4, and since there's an ordered pair, you're going to use a bracket, and then it keeps going all the way until, can you tell it's right in the middle of those 2? And since it's counting by 2s, I think it's 3. Sure would help if they gave me ordered pairs, though, wouldn't it? How about the range? The range is the lowest y value, or the output, to the highest output. So -6 with a bracket again, and then all the way up until, I'm thinking 5. Yeah. And classic algebra 2 mistake. What happens when you reverse your interval and you say 5 to -6? You get it wrong. Yeah, it's a nice way of saying it. That's a concept mistake. That's a big concept mistake, right? Intervals are always least to greatest. Oh, that one's fun. How far to the left does it go? Positive? Oh, of course, negative. And infinities always have parentheses, so -infinity, and then it stretches all the way until what right value? 4 with an endpoint, so we give it a bracket. How about range? How low does it go? -infinity. How high will it go? This time it is counting by 1, so it is a 3. Very good. They like to shake it up. Isn't that fun? Oh my goodness, for all the bonus points in my heart, who can come up with domain for 5? You can keep your bonus points, Abruzzo. Do you remember how we say, like, pretty much everything except for that one number? How do you jump over 0? The union thing, very good. So -infinity to 0, but you can't have 0 because I see there's what's called a vertical asymptote, a type of discontinuity. And then union. And then you pick up again at 0 on the other side of it, and then go on for infinity. So be inspired by that and give me your range. How low does it go? -infinity. And this, we have the same issue, but this time we have a horizontal asymptote for a discontinuity. So 0 is a problem horizontally, or sorry, on your vertical as well. So -infinity to can't do 0, so jump over it. 0 to infinity. Nice. All right, we'll stop that lesson there. You do not have to start on the homework assignment for 1.2 yet. That'll be tomorrow's assignment.